In the depths of space, scattered throughout our galaxy like cosmic lighthouses, exist objects so extraordinary that they challenge our understanding of physics itself. These are millisecond pulsars, neutron stars that rotate with such incredible speed that they complete an entire revolution in mere thousandths of a second. The fastest known millisecond pulsar, PSR J1748-2446ad, spins at an almost incomprehensible rate of 716 rotations per second. To put this in perspective, this stellar remnant, containing more mass than our entire sun compressed into a sphere barely 20 kilometers across, rotates faster than the blades of a kitchen blender. The existence of such rapidly spinning objects represents one of the most extreme manifestations of physics in the observable universe. These stellar corpses are the remnants of massive stars that have undergone catastrophic collapse, compressing matter to densities so extreme that a teaspoon would weigh as much as Mount Everest. Yet somehow, these incredibly dense objects maintain structural integrity while spinning at rates that would tear apart any normal material through sheer centrifugal force. Understanding how millisecond pulsars achieve and maintain such extraordinary rotation rates requires exploring some of the most fundamental principles of physics. The story involves stellar evolution, gravitational collapse, conservation of angular momentum, and the exotic behavior of matter under conditions that cannot be replicated anywhere on Earth. It reveals a universe where the impossible becomes routine, where physics pushes against its own theoretical limits to create phenomena that seem to belong in the realm of science fiction. The discovery of millisecond pulsars revolutionized our understanding of stellar evolution and the ultimate fate of massive stars. When astronomers first detected these cosmic speedsters in the 1980s, they opened a window into physics so extreme that it challenged existing theories about what matter could withstand. The fact that these objects exist at all represents a triumph of nature's ability to create stable configurations under the most hostile conditions imaginable. These rotating neutron stars emit beams of electromagnetic radiation from their magnetic poles, sweeping across space like the beam from a lighthouse. When these beams cross Earth's line of sight, we detect them as incredibly precise pulses of radio waves, X-rays, or gamma rays. The timing of these pulses is so regular that millisecond pulsars serve as some of the most accurate clocks in the universe, keeping time with precision that rivals the best atomic clocks ever built by human technology. Implications of millisecond pulsar research extend far beyond academic curiosity. These objects serve as natural laboratories for testing Einstein's theory of general relativity under extreme conditions, provide insights into the fundamental nature of matter at nuclear densities, and offer unique tools for detecting gravitational waves rippling through spacetime itself. They represent the intersection of astrophysics, nuclear physics, and fundamental physics, creating opportunities to study phenomena that exist nowhere else in the known universe. The story of how a star can evolve to spin 700 times per second begins with the life cycle of massive stars and ends with some of the most exotic objects in the cosmos. Along the way, we encounter physics so extreme that it challenges human comprehension while remaining firmly grounded in mathematical precision and observational evidence. This is the story of matter pushed to its absolute limits, of rotation speeds that approach the theoretical maximum allowed by physics, and of cosmic objects that serve as natural laboratories for exploring the fundamental laws that govern our universe. To understand how millisecond pulsars achieve their incredible rotation rates, we must first examine the basic properties of neutron stars themselves. These objects represent matter in one of its most extreme possible states, compressed to densities that exceed even the nuclei of atoms. The physics governing their behavior operates at the intersection of quantum mechanics, general relativity, and nuclear physics, creating conditions that are simultaneously foreign to everyday experience and precisely describable through mathematical frameworks developed over decades of theoretical and observational research. The journey from ordinary star to millisecond pulsar involves multiple phases of stellar evolution, catastrophic collapse events, and interactions with companion stars that can span billions of years. The end result is an object so compact that its surface gravity exceeds Earth's by a factor of several billion, yet so precisely balanced that it can maintain stable rotation at rates that would destroy any conventional material. Understanding this remarkable transformation requires exploring some of the most fundamental questions about the nature of matter, energy, and spacetime itself. The discovery of millisecond pulsars also opened new avenues for astronomical observation and fundamental physics research. These objects emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays, providing multiple windows for studying their properties and behavior. Their incredible rotational stability makes them ideal tools for precision timing experiments, while their extreme magnetic fields create laboratories for studying magnetospheric physics under conditions impossible to achieve on Earth. Perhaps most remarkably, millisecond pulsars demonstrate that the universe naturally creates objects operating at the very limits of what physics allows. Their rotation rates approach the theoretical maximum for neutron stars spin any faster, and centrifugal forces would overcome gravitational binding, tearing the star apart. Their magnetic field strengths reach values that would be considered impossibly large in terrestrial contexts. Their densities exceed those found in atomic nuclei, creating matter in states that challenge our understanding of how particles interact under extreme conditions. The study of millisecond pulsars thus represents more than just an investigation of exotic astronomical objects. It provides insights into the fundamental nature of matter, energy, space, and time under conditions that push physics to its absolute limits. These cosmic laboratories allow us to test theories and explore phenomena that could never be studied in terrestrial settings, revealing aspects of the universe that would otherwise remain forever hidden from direct investigation. The discovery of cosmic speedsters, the first millisecond pulsar, was discovered on November 9, 1982, by astronomer Donald Backer and his colleagues at the Arecibo Observatory in Puerto Rico. Using the massive 305-meter radio telescope, they detected a signal unlike anything previously observed in the cosmos: regular pulses of radio waves arriving at Earth with a period of just 1.337 milliseconds. This meant they had discovered an object completing 640 to full rotations every second, spinning faster than any known astronomical object. The discovery came as a complete surprise to the astronomical community. While ordinary pulsars had been known since 1967, they typically rotated much more slowly, with periods ranging from seconds to minutes. The fastest pulsar known at the time had a period of about 33 milliseconds, already considered remarkably fast. The new object, designated PSR J1748-2446ad, shattered all previous records and immediately raised fundamental questions about what kinds of objects could maintain such extreme rotation rates. The technical challenges involved in detecting millisecond pulsars pushed radio astronomy to its limits. The rapid succession of pulses required unprecedented timing precision and data processing capabilities. Radio telescopes had to be equipped with sophisticated digital systems capable of recording and analyzing signals with microsecond accuracy. The detection of PSR J1747+21 required months of careful observation and data analysis to confirm that the signals were genuinely astronomical rather than terrestrial interference. Initial skepticism about the discovery centered on whether any physical object could actually rotate at such extreme rates without flying apart. Simple calculations suggested that centrifugal forces at 642 rotations per second would overcome the gravitational binding energy of ordinary matter, causing rapid disintegration. The fact that stable rotation was observed implied the existence of material with properties far exceeding anything found on Earth, matter compressed to densities rivaling those inside atomic nuclei. The confirmation of PSR J1747+21's astronomical nature came through careful analysis of its radio signals and their behavior over time. The pulses showed the characteristic signatures of pulsar emission: highly polarized radio waves, frequency-dependent pulse profiles, and timing behavior consistent with rotation of a highly magnetized neutron star. Most convincingly, the pulsar showed gradual spin down over time due to the loss of rotational energy through electromagnetic radiation behavior predicted by theoretical models of rotating magnetized neutron stars. The discovery triggered an intensive search for additional millisecond pulsars using radio telescopes around the world. Within a few years, astronomers had identified several more of these ultra-fast rotators, each providing new insights into the physics of extreme rotation. The growing catalog of millisecond pulsars revealed a population of objects that, while rare, represented a significant component of the neutron star population in our galaxy. The second millisecond pulsar, PSR J1748-2446-09, was discovered in 1986 at the Arecibo Observatory with a period of 5.36 milliseconds. This discovery confirmed that PSR B1937+21 was not a unique anomaly, but rather represented a new class of neutron stars with fundamentally different properties from ordinary pulsars. The timing characteristics of PSR B1855+09 showed the same remarkable stability observed in the first millisecond pulsar, suggesting that all members of this class possess similar physical properties. By 1990, astronomers had discovered approximately a dozen millisecond pulsars, each contributing to our understanding of these exotic objects. The Parkes 64-meter radio telescope in Australia emerged as particularly effective for millisecond pulsar searches due to its southern hemisphere location and advanced digital signal processing capabilities. The surveys conducted at Parkes revealed that millisecond pulsars were distributed throughout the galactic disk and halo, unlike young pulsars which are concentrated near regions of active star formation. The development of specialized search techniques for millisecond pulsars required advances in both hardware and software capabilities. Traditional pulsar search methods, optimized for the longer periods and stronger signals of ordinary pulsars, were poorly suited for detecting the rapid, weak signals characteristic of millisecond pulsars. New algorithms had to be developed to handle the increased computational load of searching for signals with periods measured in milliseconds rather than seconds. Acceleration searches became crucial for detecting millisecond pulsars in binary systems, where orbital motion creates Doppler shifts that can smear out the periodic signal during long observations. These searches require examining thousands of possible acceleration values for each candidate signal, dramatically increasing the computational requirements but enabling detection of binary millisecond pulsars that would otherwise remain hidden. The development of fast Fourier transform techniques and parallel processing enabled these computationally intensive searches to become routine. The recognition that millisecond pulsars represented recycled neutron stars came gradually through the accumulation of observational evidence. The discovery of the first binary millisecond pulsar, PSR B1913+16, provided crucial evidence for the recycling scenario by demonstrating that these objects could exist in closed binary systems with evo of stellar companions. The orbital characteristics of this system, a circular orbit with a white dwarf companion, matched theoretical predictions for the end products of mass transfer evolution. Radio frequency interference represented major challenges for millisecond pulsar searches, particularly as human-generated radio emissions became increasingly prevalent throughout the frequency bands used for astronomy. The rapid rotation periods of millisecond pulsars made their signals particularly susceptible to interference from radar systems, satellite communications, and terrestrial broadcasting. Sophisticated RFI mitigation techniques had to be developed to distinguish genuine astronomical signals from the growing background of artificial radio emissions. The international nature of millisecond pulsar research became apparent as discoveries accumulated at observatories worldwide. The Jodrell Bank Observatory in the United Kingdom, the Westerbork Synthesis Radio Telescope in the Netherlands, and the Very Large Array in New Mexico all contributed significant discoveries to the growing catalog. This global effort was necessary because millisecond pulsars are faint objects requiring large telescopes and long observation times, while their random distribution across the sky meant that no single observatory could conduct comprehensive surveys. Data processing and analysis techniques evolved rapidly to handle the unique characteristics of millisecond pulsar signals. Unlike ordinary pulsars, which produce relatively strong individual pulses that can be detected in real time, millisecond pulsars typically require integration of hundreds or thousands of weak pulses to achieve detectable signal-to-noise ratios. This necessitated the development of sophisticated folding algorithms that could maintain phase coherence over long integration times while compensating for various systematic effects. The naming convention for these objects reflects both their discovery circumstances and their remarkable properties. The designation millisecond pulsar indicates objects with rotation periods measured in milliseconds, typically defined as having periods less than about 30 milliseconds. This arbitrary cutoff distinguishes them from ordinary pulsars while recognizing that the physics governing their behavior operates along a continuum of rotation rates and stellar properties. Early observations of millisecond pulsars revealed several surprising characteristics that distinguished them from their slower spinning cousins. Most importantly, they showed much more stable timing than ordinary pulsars, with rotation periods that remained constant to extraordinary precision over long observation periods. This timing stability suggested that millisecond pulsars had somehow reached a state of rotational equilibrium, no longer undergoing the rapid spin-down characteristic of young neutron stars. The magnetic field strengths inferred for millisecond pulsars were typically much lower than those of ordinary pulsars, typically 108 to 109 Tesla compared to 1012 Tesla for young pulsars. This observation provided the first clue to understanding how these objects might achieve such extreme rotation rates while maintaining long-term stability. Lower magnetic fields meant reduced electromagnetic braking, allowing rapid rotation to persist over billions of years. The spatial distribution of millisecond pulsars in our galaxy also differed significantly from that of ordinary pulsars. While young pulsars are concentrated in the galactic disk where massive star formation occurs, millisecond pulsars show a more spherical distribution characteristic of old stellar populations. This suggested that millisecond pulsars represented an evolved phase of neutron star development, rather than the immediate aftermath of stellar collapse. The discovery of millisecond pulsars in binary systems provided crucial insights into their formation mechanism. Many of the early discoveries showed evidence of orbital motion around low-mass companion stars, indicating that binary interactions played a crucial role in the spin-up process. The orbital characteristics of these systems, tight circular orbits with periods of hours to days, suggested that the neutron stars had accreted matter from evolved companion stars over extended periods. Radio observations revealed that millisecond pulsars emit their characteristic pulses across a wide range of frequencies, from about 100 MHz to several GHz. The pulse profiles and polarization characteristics vary significantly with observing frequency, indicating complex emission mechanisms operating in the intense magnetic field and radiation environment. Near the neutron star surface, understanding these emission processes requires sophisticated modeling of plasma physics under extreme conditions. The discovery of millisecond pulsars also opened new possibilities for using neutron stars as tools for fundamental physics research. Their extraordinary timing stability made them ideal candidates for detecting tiny perturbations caused by gravitational waves, changes in Earth's rotation, or irregularities in atomic time standards. Within a decade of their discovery, millisecond pulsars were being used for some of the most precise timing experiments ever attempted in astronomy. The search techniques developed for finding millisecond pulsars pushed the boundaries of signal processing and data analysis. The short periods meant that signals could be easily masked by radio frequency interference, scintillation effects in the interstellar medium, or instrumental artifacts. Sophisticated algorithms were developed to distinguish genuine pulsar signals from the myriad sources of contamination that plague radio astronomical observations. By the end of the 1980s, the discovery of millisecond pulsars had fundamentally changed our understanding of neutron star physics and stellar evolution. These objects demonstrated that nature could create stable configurations of matter rotating at rates that approached the theoretical limits imposed by general relativity. Their existence confirmed theoretical predictions about neutron star recycling through binary interactions while opening new avenues for studying fundamental physics under extreme conditions. The continuing discovery of millisecond pulsars through systematic radio surveys has revealed a rich population of these objects throughout our galaxy. Current estimates suggest that there may be tens of thousands of millisecond pulsars in the Milky Way, most too faint or poorly positioned to be detected with current technology. Each new discovery adds to our understanding of how these remarkable objects form, evolve, and interact with their environments over cosmic timescales. The physics of neutron star rotation. Understanding how neutron stars can rotate 700 times per second requires examining the fundamental physics that governs these extraordinary objects. Neutron stars represent matter in one of its most extreme possible states, atomic nuclei compressed to densities exceeding those found inside the protons and neutrons themselves. At such densities, ordinary concepts of solid matter break down, replaced by exotic phases of nuclear matter that exist nowhere else in the observable universe. The basic structure of a neutron star consists of several distinct layers, each characterized by different physical properties and compositions. The outermost layer is a solid crust composed primarily of neutron-rich atomic nuclei arranged in a crystalline lattice structure. Below this crust lies the outer core, where atomic nuclei dissolve into a sea of neutrons, protons, and electrons. At the very center may exist even more exotic forms of matter, possibly including hyperons, kaons, or quark matter in configurations that push our understanding of particle physics to its limits. The incredible density of neutron star matter, typically exceeding kilograms per cubic centimeter, creates gravitational fields so intense that they significantly warp spacetime around the star. General relativistic effects become crucial for understanding neutron star structure and behavior, influencing everything from the maximum possible mass to the relationship between rotational energy and degravitational binding. The balance between gravitational attraction and the pressure of degenerate nuclear matter determines the star's radius and internal structure. Conservation of angular momentum provides the key to understanding how neutron stars achieve such extreme rotation rates. When a massive star collapses to form a neutron star, its radius decreases by a factor of approximately 100,000, from roughly 700,000 kilometers to about 20 kilometers. Since angular momentum must be conserved during this collapse, the rotation rate increases by the square of the radius reduction factor, potentially reaching rotation periods of milliseconds even if the original star rotated relatively slowly. However, conservation of angular momentum alone cannot explain the existence of millisecond pulsars. Most neutron stars are born with rapid rotation, but electromagnetic breaking through their intense magnetic fields causes them to spin down over time scales of millions of years. Young pulsars typically have strong magnetic fields of 10-12 Tesla or more, creating powerful electromagnetic torques that rapidly reduce their rotation rates. To maintain millisecond periods requires either unusually weak magnetic fields or a mechanism for re-accelerating the neutron star's rotation. The solution to this puzzle lies in binary stellar evolution and the process known as neutron star recycling. When a neutron star exists in a closed binary system with a normal star, gravitational interactions can cause matter to flow from the companion onto the neutron star's surface. This accretion process not only adds mass to the neutron star but also transfers angular momentum, potentially spinning it up to rotation periods of milliseconds. The accreted material must overcome the neutron star's magnetic field to reach the surface, a process that typically weakens the field through magnetic field line reconnection and burial. The physics of matter accretion onto rapidly rotating neutron stars involves complex interactions between gravity, magnetic fields, and plasma dynamics. As material falls toward the neutron star, it forms an accretion disk similar to those found around black holes, but with important differences due to the neutron star's solid surface and intense magnetic field. The magnetic field channels accreting material toward the magnetic poles, creating hot spots that emit intense X-ray radiation as the material impacts the surface at velocities approaching significant fractions of the speed of light. The maximum rotation rate that a neutron star can sustain is limited by the balance between gravitational binding and centrifugal force. As rotation speed increases, material at the neutron star's equator experiences increasing centrifugal acceleration that opposes gravitational attraction. The critical rotation rate, known as the Keplerian frequency, occurs when centrifugal force exactly balances gravity at the equatorial surface. Rotation faster than this critical rate would cause the neutron star to lose mass from its equator, making stable rotation impossible. For typical neutron star masses N/d, the Keplerian frequency corresponds to rotation periods of roughly 0.5 to 1.0 milliseconds, depending on the detailed equation of state for nuclear matter. The fastest observed millisecond pulsars, with periods around 1.4 milliseconds, operate at roughly 60 to 70% of this theoretical maximum. The fact that no pulsars are observed rotating faster than about 1.0 millisecond provides important constraints on neutron star structure and the properties of matter at nuclear densities. The internal structure of rapidly rotating neutron stars differs significantly from that of slowly rotating or non-rotating configurations. Centrifugal forces cause the star to become oblate, with the equatorial radius exceeding the polar radius by several percent for the fastest rotators. This deformation affects the star's moment of inertia and gravitational field, creating complex interactions between rotation, gravitational binding, and internal pressure that must be calculated using sophisticated numerical methods. The exotic matter phases that may exist in neutron star cores become particularly important for understanding rapid rotation. Different theoretical models for the nuclear equation of state predict different maximum masses N/d for neutron stars, directly affecting the maximum sustainable rotation rates. Observations of millisecond pulsars thus provide important tests of nuclear physics theory under conditions that cannot be replicated in terrestrial laboratories. Superfluidity and superconductivity in neutron star interiors add additional complexity to the physics of rapid rotation. Theoretical models predict that neutrons in the core may form a superfluid, while protons may exhibit superconducting behavior. These quantum mechanical effects influence how angular momentum is transferred between different components of the neutron star, potentially affecting spin evolution and creating phenomena such as pulsar glitches. Sudden increases in rotation rate thought to result from superfluid decoupling and recoupling. The magnetic field structure of millisecond pulsars presents another fascinating aspect of neutron star physics. While these objects have relatively weak surface magnetic fields compared to young pulsars, they still maintain fields of 108 to key Tesla intensities that would be considered extraordinarily strong. In terrestrial contexts, the interaction between rotation and magnetic field creates a complex magnetosphere populated by charged particles accelerated to relativistic energies, producing the characteristic pulse emission observed from Earth. The emission mechanism responsible for pulsar radiation remains an active area of theoretical research. The leading model involves charged particles accelerated along magnetic field lines in the neutron star's magnetosphere, creating coherent radio emission through various plasma instabilities and wave particle interactions. The extreme conditions in millisecond pulsar magnetospheres with magnetic fields of 10^8 Tesla and rotation rates of hundreds of hertz create laboratory conditions for plasma physics that exist nowhere else in the accessible universe. Energy loss mechanisms for millisecond pulsars differ significantly from those operating in young pulsars. While young pulsars lose energy primarily through magnetic dipole radiation, millisecond pulsars with their weaker magnetic fields experience much reduced electromagnetic braking. Other energy loss mechanisms, such as gravitational wave emission from small asymmetries in the neutron star's mass distribution, may become relatively more important for these objects. The long-term evolution of millisecond pulsars depends on the complex interplay between various physical processes operating over timescales of billions of years. Continued accretion from binary companions can further spin up the neutron star, while magnetic field evolution, crustal cracking, and nuclear reactions in the deep interior all influence the star's rotational behavior. Understanding these evolutionary processes requires combining insights from stellar astrophysics, nuclear physics, plasma physics, and general relativity in ways that push theoretical modeling to its limits. Stellar evolution and neutron star formation. The story of how a millisecond pulsar comes to exist begins not with exotic nuclear physics or extreme rotation, but with the ordinary life and death of massive stars scattered throughout our galaxy. Understanding the formation of neutron stars requires tracing stellar evolution from the initial collapse of interstellar gas clouds through nuclear burning phases that span millions of years. culminating in one of the most violent events in the universe, a core collapse supernova explosion. Neutron stars form from the cores of massive stars that have exhausted their nuclear fuel and can no longer support themselves against gravitational collapse. The minimum mass for neutron star formation is approximately 8 solar masses, though the exact threshold depends on factors such as stellar rotation, magnetic fields, and metallicity. Stars below this mass limit end their lives as white dwarf stars, while those above approximately 25 solar masses may collapse directly to black holes without forming stable neutron stars. The evolutionary path to neutron star formation involves multiple stages of nuclear burning that progressively create heavier elements in the stellar core. Massive stars begin by fusing hydrogen into helium in their cores, a process that can continue for several million years depending on the star's mass. As hydrogen becomes depleted, the core contracts and heats until helium fusion begins, creating carbon and oxygen. This pattern continues through successive burning phases: carbon burning, neon burning, oxygen burning, each occurring at higher temperatures and densities as the stellar core becomes increasingly compressed. The final nuclear burning phase involves silicon fusion, which rapidly produces iron peak elements in the stellar core. Iron represents the most tightly bound atomic nucleus, meaning that both fusion and fission of iron nuclei require energy input rather than releasing energy. When the core reaches a critical mass approximately 1 point for solar masses, known as the Chandrasekhar limit, electron degeneracy pressure can no longer support the core against gravitational collapse, and catastrophic collapse ensues. Core collapse occurs on timescales of milliseconds to seconds, representing one of the most rapid and violent processes in astrophysics. As the iron core collapses, atomic nuclei are crushed together until protons and electrons are forced to combine into neutrons through inverse beta decay reactions. The core density rises from typical nuclear density to several times nuclear density in a fraction of a second, while the temperature soars to tens of billions of Kelvin. The collapse halts when nuclear forces become repulsive at densities exceeding that of atomic nuclei, causing the infalling matter to bounce off the newly formed neutron star core. This bounce creates a shock wave that propagates outward through the stellar envelope, potentially ejecting the star's outer layers in a supernova explosion. The energy released in this process, approximately 1044 joules, represents one of the most energetic events in the observable universe, briefly outshining entire galaxies. The newly formed neutron star that remains after the supernova explosion is initially extremely hot and rapidly rotating. The conservation of angular momentum during collapse means that even slowly rotating massive stars can produce neutron stars with rotation periods of milliseconds to seconds. However, the intense magnetic fields generated during the collapse, typically 1012 to 1015 Tesla, create electromagnetic torques that rapidly spin down the neutron star over timescales of thousands to millions of years. Most neutron stars are born as isolated objects, having been ejected from binary systems by the asymmetric supernova explosion or having formed from single massive stars. These isolated neutron stars undergo rapid spin-down due to their strong magnetic fields and are observed as young pulsars with periods ranging from milliseconds to seconds. Without external torques to maintain their rotation, these objects eventually spin down to periods of many seconds and become too faint to detect with current radio telescopes. The formation of millisecond pulsars requires a different evolutionary pathway that involves binary stellar interactions. When a neutron star exists in a closed binary system with a less massive companion star, stellar evolution can lead to mass transfer episodes that dramatically alter the neutron star's rotational state. As the companion star evolves and expands beyond its Roche load, matter begins flowing from the companion onto the neutron star through an accretion disk. The accretion process serves multiple functions in creating millisecond pulsars. First, the accreted matter carries angular momentum that can spin up the neutron star to rotation periods of milliseconds. Second, the accreting material tends to bury and weaken the neutron star's magnetic field through flux freezing and field line reconnection processes. Third, the accretion energy heats the neutron star surface, making it observable as a bright X-ray source during active accretion phases. The companion stars in millisecond pulsar systems are typically low-mass objects, either main sequence stars with masses less than 1 solar mass or evolved white dwarf stars. These systems represent the end products of common envelope evolution, where the neutron star and its companion underwent a phase of close interaction that ejected the envelope of a more massive progeny star. The resulting tight binary systems have orbital periods ranging from hours to days and are ideally configured for sustained mass transfer. Different types of companion stars create different classes of millisecond pulsar systems, with main sequence companions are observed during active accretion phases as low-mass X-ray binaries, characterized by bright X-ray emission from the heated neutron star surface and accretion disk. When the companion star exhausts its envelope mass or moves away from its Roche lobe, accretion ceases and the system becomes visible as a millisecond pulsar in a circular orbit around a helium-white dwarf companion. Spider systems represent an extreme category of millisecond pulsar binaries where the neutron star's intense radiation and particle wind gradually ablate the low-mass companion star. These systems are subdivided into black widow pulsars, with companion masses less than 0.05 solar masses, and redback pulsars, with companion masses between 0.1 and 0.4 solar masses. The ongoing ablation process creates clouds of material around these systems and may eventually lead to the complete destruction of the companion star. The magnetic field evolution of neutron stars during the recycling process remains an active area of theoretical research. Observations suggest that millisecond pulsars have magnetic field strengths typically 100 to 1,000 times weaker than those of young pulsars. But the physical mechanisms responsible for this field decay are not fully understood. Proposed explanations include ohmic decay in the neutron star crust, field burial by accreted material, and magnetic reconnection processes in the accretion disk. The duration of the accretion phase required to spin up a neutron star to millisecond periods depends on the accretion rate and the initial rotation state of the neutron star. Theoretical models suggest that accretion of approximately 0.1 to 0.2 solar masses over timescales of 100 million to 1 billion years can spin up a neutron star from periods of seconds to periods of milliseconds. This implies that the accretion phase is a relatively brief episode in the neutron star's overall evolutionary history. The formation rate of millisecond pulsars in our galaxy depends on the statistics of massive star formation, supernova explosion rates, and the fraction of neutron stars that participate in successful binary evolution. Current estimates suggest that millisecond pulsars are formed at rates of roughly 1 per million years in galaxies similar to the Milky Way. The total population of millisecond pulsars in our galaxy may reach tens of thousands of objects, most of which remain undetected due to observational limitations. Population synthesis models that simulate the formation and evolution of large numbers of binary systems provide insights into the statistical properties of millisecond pulsar populations. These models incorporate stellar evolution theory, binary interaction physics, and observational constraints to predict the distributions of orbital periods, companion masses, and system ages that should be observed. Comparisons between model predictions and observed pulsar populations provide tests of our understanding of stellar evolution and neutron star physics. The chemical composition of millisecond pulsars may differ from that of isolated neutron stars due to the accretion of processed material from evolved companion stars. The accreted material is enriched in helium, carbon, oxygen, and heavier elements produced by nucleosynthesis in the companion star's interior. This compositional difference may affect the neutron star's cooling rate, magnetic field evolution, and long-term stability, though these effects remain poorly understood. The recycling process, how neutron stars become millisecond pulsars. The transformation of an ordinary pulsar into a millisecond pulsar represents one of the most remarkable recycling processes in the universe. This metamorphosis requires billions of years and involves complex interactions between two stars locked in an intimate gravitational dance. Understanding this recycling process illuminates how nature can rejuvenate ancient stellar corpses, spinning them up to rotation rates that approach the limits of what physics allows. The recycling scenario begins with a massive star and a less massive companion orbiting each other in a binary system. The more massive star evolves more rapidly, exhausting its nuclear fuel and undergoing core collapse to form a neutron star. The supernova explosion that creates the neutron star typically disrupts the binary system due to mass loss and asymmetric explosion effects. But in some cases, perhaps 10% to 20% of neutron star births, the binary system remains bound with the neutron star and companion star continuing to orbit each other. Initially, the newly formed neutron star behaves like any young pulsar. It possesses a strong magnetic field of approximately 1012 Tesla and rotates rapidly due to conservation of angular momentum during the core collapse. The neutron star emits beams of electromagnetic radiation from its magnetic poles, sweeping across space like a cosmic lighthouse. If these beams cross Earth's line of sight, the object is detectable as a radio pulsar with a period typically ranging from milliseconds to seconds. Over the following millions of years, the neutron star gradually spins down due to electromagnetic braking. The strong magnetic field creates a torque that extracts rotational energy from the neutron star, converting it into electromagnetic radiation and high-energy particles that escape into interstellar space. This spin-down process is observed in young pulsars throughout our galaxy, with rotation periods increasing at predictable rates determined by the strength of the magnetic field and the rate of rotational energy loss. Eventually, the neutron star spins down to the point where its radio emission becomes too weak to detect with current telescopes. The pulsar effectively dies as an observable object, though it continues to exist as a weakly magnetized, slowly rotating neutron star. Without the recycling process, this would represent the end of the neutron star's active life as a pulsar. However, binary evolution provides a mechanism for rejuvenating these stellar corpses and returning them to active duty as millisecond pulsars. The recycling process begins when the companion star evolves and expands to fill its row, the region of space around each star where its gravitational field dominates. As stellar evolution progresses, the companion star's outer layers expand due to nuclear burning in its core or envelope. When the stellar surface reaches the Roslow boundary, gravitational forces from the neutron star begin to strip material from the companion's outer layers, initiating mass transfer between the two stars. Mass transfer in binary systems creates one of the most spectacular phenomena in astrophysics. Material flowing from the companion star cannot fall directly onto the neutron star due to conservation of angular momentum. Instead, the accreting matter forms a disk-like structure around the neutron star, gradually spiraling inward as angular momentum is redistributed through viscous processes within the disk. This accretion disk becomes heated to temperatures of millions of degrees through gravitational potential energy release, making it observable as a bright X-ray source. The X-ray luminosity of accreting neutron stars can exceed the luminosity of our Sun by factors of thousands to tens of thousands, making them among the brightest objects in the X-ray sky. These systems are classified as low-mass X-ray binaries when the companion star has a mass less than 1 solar mass, or high-mass X-ray binaries when the companion exceeds 1 solar mass. The majority of recycled millisecond pulsars appear to originate from low-mass X-ray binary systems with orbital periods ranging from hours to days. The accretion process serves multiple crucial functions in the recycling scenario. Most importantly, the accreting material carries angular momentum that is transferred to the neutron star through magnetic field interactions and disk magnetosphere coupling. As material spirals inward through the accretion disk, it reaches increasingly high velocities approaching significant fractions of the speed of light. When this rapidly rotating material interacts with the neutron star's magnetosphere, it exerts a torque that spins up the neutron star's rotation. The amount of angular momentum transfer depends on the mass accretion rate, the magnetic field strength, and the detailed physics of disk magnetosphere interaction. Theoretical models suggest that accretion rates of 10 to 10 to -8 solar masses per year over timescales of 100 million to 1 billion years can spin up a neutron star from periods of seconds to periods of milliseconds. This requires the accretion of approximately 0.1 to 0.2 solar masses of material, roughly 10% to 20% of the neutron star's original mass. The magnetic field evolution during the recycling process represents one of the most important and least understood aspects of millisecond pulsar formation. Observations consistently show that millisecond pulsars have magnetic field strengths approximately 100 to 1,000 times weaker than those of young pulsars. This dramatic field reduction is crucial for the recycling process, as strong magnetic fields would prevent matter from reaching the neutron star surface and would create electromagnetic torques that oppose spin-up. Several physical mechanisms have been proposed to explain magnetic field decay during accretion. Ohmic dissipation in the neutron star's crust may cause the magnetic field to decay over timescales of millions to billions of years, though the conductivity of crustal material under extreme conditions remains poorly constrained. Field burial bioaccreted material may physically cover magnetic field lines, reducing the external field strength while preserving flux in the neutron star interior. Magnetic reconnection processes in the accretion disk may also contribute to field evolution, as accreted material interacts with magnetic field lines threading the disk. Complex magnetohydrodynamic instabilities can develop that reconfigure the field geometry and reduce the net magnetic flux out, inking the neutron star to its surrounding environment. These processes operate in regimes of magnetic field strength, density, and temperature that have no terrestrial analogs. The transition from accreting X-ray source to millisecond pulsar occurs when mass transfer from the companion star ceases or drops below a critical threshold. This transition may result from the companion star shrinking below its Roche lobe as stellar evolution proceeds, from changes in the orbital configuration due to gravitational wave emission or magnetic braking, or from complete exhaustion of the companion star's envelope mass. When accretion ceases, the neutron star's rotation is no longer supported by angular momentum transfer, and it begins to behave as an ordinary pulsar. However, the recycled neutron star now possesses dramatically different properties from its original state. The weak magnetic field means that electromagnetic braking is greatly reduced, allowing rapid rotation to persist for billions of years rather than spinning down over millions of years. The millisecond rotation period reflects the cumulative effect of billions of years of spin-up through accretion. These properties combine to create the observed characteristics of millisecond pulsars: extremely stable rotation, weak magnetic fields, and rotation periods measured in milliseconds. Binary millisecond pulsars retain their companion stars and provide direct evidence for the recycling scenario. These systems typically contain low-mass white dwarf companions in tight circular orbits around the neutron star. The white dwarf represents the core of the original companion star, stripped of its hydrogen and helium envelope during the mass transfer phase. The circular orbits result from tidal circularization during the accretion phase, when the binary separation was comparable to the stellar radius. Isolated millisecond pulsars may result from systems where the companion star was completely destroyed during the accretion process, or where the binary was disrupted by external interactions such as encounters with other stars in dense stellar environments. Spider pulsar systems, black widows, and redbacks represent cases where the millisecond pulsar's intense radiation and particle wind are gradually ablating a low-mass companion star, potentially leading to complete companion destruction over cosmic timescales. The recycling process is not perfectly efficient, and many details remain uncertain due to the complexity of the underlying physics. The fraction of neutron stars that successfully undergo recycling depends on binary evolution statistics, mass transfer stability, and magnetic field evolution, all areas where theoretical models must be calibrated against observational constraints. Population synthesis calculations suggest that perhaps 1% to 10% of neutron stars undergo successful recycling to become observable millisecond pulsars. Recent observations have revealed transitional millisecond pulsar systems that switch between accretion-powered X-ray emission and rotation-powered radio emission on timescales of months to years. These systems provide unique laboratories for studying the recycling process in real time, revealing how neutron stars transition between different states of activity as accretion rates fluctuate. Understanding these transitional objects may provide crucial insights into the detailed physics governing neutron star recycling. The discovery of millisecond pulsars in globular clusters has provided additional evidence for the recycling scenario. These ancient stellar systems contain high densities of evolved stars and frequent stellar interactions that can modify binary evolution. The enhanced formation rates of millisecond pulsars in globular clusters compared to the galactic disk strongly supports the binary recycling model and demonstrates the importance of stellar encounters in shaping pulsar populations. The extreme physics of ultra-rapid rotation. When a neutron star spins 700 times per second, it operates in a regime of physics that pushes matter to its absolute limits. The combination of extreme density, intense magnetic fields, and ultra-rapid rotation creates conditions that exist nowhere else in the observable universe, allowing scientists to study fundamental physics under circumstances impossible to replicate in terrestrial laboratories. Understanding the extreme physics of millisecond pulsars requires examining how matter behaves when subjected to gravitational fields billions of times stronger than Earth's while rotating at speeds that approach the theoretical maximum allowed by general relativity. The surface of a millisecond pulsar rotating at 700 Hz experiences centrifugal acceleration of approximately km per second squared, roughly 100 million times Earth's surface gravity. Despite this enormous centrifugal force, the neutron star's gravitational field is so intense that it easily retains its material. The surface gravity of a typical neutron star exceeds km per second squared, meaning that gravitational acceleration dominates centrifugal effects by factors of 100 to 1000 even for the most rapidly rotating millisecond pulsars. The balance between gravitational attraction and centrifugal repulsion determines the maximum possible rotation rate for neutron stars. As rotation speed increases, centrifugal forces become increasingly important, particularly near the neutron star's equator where rotational velocity reaches its maximum. The critical rotation frequency known as the mass shedding limit or Keplerian frequency occurs when centrifugal force exactly balances gravitational attraction at the equatorial surface, making further increases in rotation rate impossible without material loss. For typical neutron star parameters, the mass shedding limit corresponds to rotation frequencies between 1000 and 2000 Hz, depending on the star's mass, radius, and internal structure. The fastest observed millisecond pulsars rotate at approximately 700 to 750 Hz, representing roughly 60 to 70% of the theoretical maximum. The fact that no pulsars are observed rotating faster than about 700 Hz provides important observational constraints on neutron star physics and the equation of state for matter. At nuclear densities, rapid rotation significantly affects the internal structure and shape of neutron stars. Centrifugal forces cause the neutron star to become oblate, with the equatorial radius exceeding the polar radius by several percent for the fastest rotators. This deformation affects the star's moment of inertia, gravitational field, and tidal interactions with binary companions. The relationship between rotation rate and oblateness provides sensitive tests of neutron star models and the properties of matter under extreme conditions. The moment of inertia of a millisecond pulsar depends on both the star's mass distribution and its rotation rate. For slowly rotating neutron stars, the moment of inertia is determined primarily by the mass and radius, similar to ordinary spherical objects. However, rapid rotation creates a complex feedback between centrifugal forces, gravitational binding, and internal pressure that must be calculated using sophisticated numerical methods that solve Einstein's field equations in the rotating reference frame. General relativistic effects become increasingly important for rapidly rotating neutron stars. The intense gravitational field causes significant frame dragging effects, where spacetime itself is twisted by the star's rotation. These effects influence the behavior of matter and electromagnetic fields near the neutron star, affecting everything from accretion disk dynamics to pulsar emission mechanisms. Frame dragging also affects the precession of orbital planes in binary systems, providing observable signatures of strong field general relativity. The equation of state for matter at nuclear densities plays a crucial role in determining the properties of rapidly rotating neutron stars. Different theoretical models for nuclear matter predict different relationships between pressure and density at the extreme conditions found in neutron star cores. These differences translate into variations in maximum mass, radius, and maximum rotation rate, making observations of millisecond pulsars important tests of nuclear physics theory. Exotic matter phases that may exist in neutron star cores become particularly relevant for understanding rapid rotation. Theoretical models predict that matter at densities several times nuclear density may undergo phase transitions to quark matter, hyperon matter, or other exotic states. These phase transitions can dramatically alter the equation of state, affecting the neutron star's ability to sustain rapid rotation and its response to centrifugal deformation. The magnetic field structure of rapidly rotating neutron stars differs significantly from that of slowly rotating or non-rotating configurations. Rapid rotation affects magnetic field evolution through magnetorotational instabilities, differential rotation effects, and coupling between magnetic field and fluid motions. The resulting magnetic field geometry may be complex, with departures from simple dipole structure that affect pulsar emission characteristics and electromagnetic braking rates. Crustal physics in rapidly rotating neutron stars involves the interaction between the solid crust and the fluid interior under extreme rotational stress. The neutron star crust is thought to form a crystalline solid composed of neutron-rich atomic nuclei in a sea of superfluid neutrons and relativistic electrons. Rapid rotation creates shear stresses in this material that may approach the breaking point, potentially leading to crustal fractures and sudden changes in rotation rate known as pulsar glitches. The superfluid properties of neutron star interiors add additional complexity to the physics of rapid rotation. Theoretical models predict that neutrons in the core form a superfluid that can rotate independently of the charged components, protons, and electrons that carry the magnetic field. This superfluid normal fluid coupling creates complex dynamics where angular momentum can be exchanged between different components on various timescales, affecting the star's response to external torques. Thermal evolution in rapidly rotating neutron stars is influenced by both rotational energy dissipation and magnetic field evolution. The combination of rapid rotation and strong magnetic fields can generate substantial heating through various dissipative processes, including magnetic reconnection, currents induced by differential rotation, and friction between superfluid and normal components. Understanding these heating mechanisms is crucial for interpreting observations of neutron star surface temperatures and cooling rates. The emission mechanisms responsible for pulsar radiation operate under extreme conditions in millisecond pulsar magnetospheres. The combination of rapid rotation and magnetic field strengths of 10^8 TeV creates regions where charged particles are accelerated to relativistic velocities along curved magnetic field lines. The resulting electromagnetic radiation spans the entire spectrum from radio waves to gamma rays, with emission characteristics that depend sensitively on the detailed magnetospheric structure. Coherent radio emission from millisecond pulsars requires the generation of organized electromagnetic waves through plasma instabilities and wave-particle interactions. The plasma physics governing these processes operates in regimes of magnetic field strength, particle density, and rotational frequency that have no terrestrial analogs. Understanding coherent emission mechanisms requires sophisticated modeling of relativistic plasma behavior in strongly magnetized, rapidly rotating systems. The stability of millisecond pulsar rotation reflects the balance between various energy gain and loss mechanisms operating over cosmic timescales. While electromagnetic braking tends to spin down the neutron star, other processes such as accretion from the interstellar medium or tidal interactions in binary systems may provide small torques that affect long-term evolution. The extraordinary timing stability of millisecond pulsars, often better than 10 to 15 in fractional frequency precision, demonstrates that these various effects are extremely well balanced. Quantum effects in the magnetospheres of rapidly rotating neutron stars may become important due to the extreme electric and magnetic field strengths. In the vicinity of the neutron star surface, electric field strengths can approach the critical value for pair production from the quantum vacuum, while magnetic field strengths may exceed the quantum critical field, where Landau level spacing becomes comparable to the particle rest mass energy. These quantum electrodynamic effects may influence particle acceleration and radiation processes in ways that are still being explored theoretically. The gravitational wave emission from rapidly rotating neutron stars represents another aspect of extreme physics that becomes accessible through millisecond pulsar observations. While perfectly symmetric neutron stars emit no gravitational waves, small asymmetries in mass distribution, perhaps as small as a few centimeters in surface height, can generate detectable gravitational radiation. The search for continuous gravitational waves from known millisecond pulsars provides tests of neutron star structure and Einstein's theory of general relativity. Observing the universe's most precise clocks. Millisecond pulsars represent the most stable natural timekeepers in the known universe, maintaining rotational precision that rivals or exceeds the best atomic clocks ever constructed by human technology. This extraordinary stability transforms these exotic astronomical objects into precision instruments capable of detecting phenomena ranging from gravitational waves to irregularities in Earth's rotation. Understanding how astronomers observe and utilize millisecond pulsars as cosmic chronometers reveals both the remarkable physics of these objects and their growing importance as tools for fundamental research. The timing stability of millisecond pulsars emerges from their unique combination of physical properties. Unlike young pulsars, which undergo rapid spin-down due to strong magnetic fields, millisecond pulsars have weak magnetic fields that produce minimal electromagnetic braking. This allows their rotation rates to remain essentially constant over timescales of years to decades, with fractional frequency changes typically less than 1 part in 1,015 per year. Such stability means that a millisecond pulsar's rotation period remains constant to better than 1 microsecond over observation spans of many years. Radio observations of millisecond pulsars require sophisticated techniques to achieve the timing precision necessary to exploit their clock-like properties. Radio telescopes must record pulsar signals with microsecond time resolution while maintaining absolute timing accuracy through connections to atomic time standards. The arrival times of individual pulses are measured relative to coordinated universal time (UTC) with uncertainties approaching 100 nanoseconds for the strongest signals. Though typical timing precision ranges from microseconds to tens of microseconds depending on the pulsar's brightness and the observing system's capabilities. The process of pulsar timing involves creating a phase-coherent model that predicts the arrival time of every pulse from a millisecond pulsar over extended observation periods. This model must account for numerous effects that influence pulse arrival times, including the pulsar's rotational evolution, binary orbital motion, interstellar propagation effects, and various relativistic corrections. The precision of modern pulsar timing allows detection of timing residuals differences between observed and predicted arrival times with accuracies approaching 10 nanoseconds. For the best timed pulsars, constructing accurate timing models for millisecond pulsars requires careful analysis of systematic effects that can mimic or mask the signals being sought. Earth's rotation and orbital motion around the Sun create predictable Doppler shifts in pulsar signals that must be corrected to high precision. The solar system's motion through the galaxy produces additional Doppler effects, while gravitational time dilation in Earth's varying gravitational field creates timing variations of several microseconds over annual timescales. Interstellar propagation effects introduce frequency-dependent delays in pulsar signals that vary with observing frequency and change slowly over time. Radio waves traveling through the ionized interstellar medium experience dispersion delays proportional to the inverse square of the observing frequency, while scattering by small-scale density fluctuations can introduce additional timing variations. Understanding and correcting for these propagation effects requires multi-frequency observations and sophisticated modeling of the interstellar medium. Binary millisecond pulsars provide additional complexity and opportunity for precision measurements. The orbital motion of the pulsar around its companion creates periodic Doppler shifts that must be modeled with extraordinary precision to achieve optimal timing performance. However, this orbital motion also enables tests of Einstein's theory of general relativity and measurements of fundamental constants through observations of relativistic effects such as periastron advance, gravitational redshift, and orbital decay due to gravitational wave emission. The most precisely timed binary millisecond pulsars allow measurement of relativistic effects with accuracies that test general relativity to unprecedented precision. The orbital decay of PSR J1748-2446, the first binary pulsar discovered, matches Einstein's prediction for gravitational wave emission to better than 0.2%, providing compelling evidence for the existence of gravitational radiation. More recent binary pulsar discoveries have enabled even more precise tests of relativistic gravity and measurements of neutron star masses with uncertainties less than 0.01 solar masses. Pulsar timing arrays represent the cutting edge of precision timing science, utilizing networks of millisecond pulsars distributed across the sky as a galaxy-scale gravitational wave detector. By monitoring dozens of millisecond pulsars simultaneously over periods of decades, astronomers can search for correlated timing residuals that would indicate the passage of gravitational waves from supermassive black hole binaries in distant galaxies. These experiments require timing precision approaching 10 nanoseconds and coordination between radio telescopes worldwide. The search for gravitational waves using pulsar timing arrays has revealed the extraordinary stability requirements necessary to detect these subtle effects. Gravitational waves from spiraling supermassive black hole binaries would create timing residuals of tens to hundreds of nanoseconds correlated across multiple pulsars in characteristic patterns, determined by the source location and gravitational wave polarization. Detecting such signals requires maintaining timing stability over decades while carefully accounting for all other sources of timing variation. Recent results from pulsar timing array experiments have begun to reveal evidence for a stochastic gravitational wave background, a sea of overlapping gravitational wave signals from numerous supermassive black hole binaries throughout the observable universe. The detection of this background represents a major milestone in gravitational wave astronomy and demonstrates the power of millisecond pulsars as tools for exploring the universe's most energetic phenomena. The instrumental requirements for precision pulsar timing have driven advances in radio astronomy technology and data processing techniques. Modern pulsar timing experiments require radio telescopes with collecting areas of thousands of square meters, low-noise receivers operating across broad frequency ranges, and digital signal processing systems capable of recording and analyzing terabits of data per observation session. The most ambitious timing experiments utilize multiple telescopes simultaneously to improve sensitivity and provide redundancy against instrumental systematics. Atomic time standards play a crucial role in pulsar timing experiments, providing the stable frequency references necessary to achieve nanosecond timing precision. The most precise pulsar timing utilizes hydrogen maser frequency standards that maintain fractional frequency stability better than 1 part in 1015 over timescales of hours to days. International Atomic Time (TI) and Terrestrial Time (TT) provide the fundamental time scales against which pulsar timing measurements are referenced, requiring careful understanding of time scale definitions and their relationships. The data analysis techniques used in pulsar timing involve sophisticated statistical methods for parameter estimation and model selection. Bayesian inference methods allow simultaneous fitting of dozens of parameters describing pulsar rotation, binary orbital elements, and various correction terms while properly accounting for measurement uncertainties and correlations between parameters. Advanced algorithms such as Markov chain Monte Carlo sampling enable exploration of high-dimensional parameter spaces and robust uncertainty quantification. Systematic effects in pulsar timing experiments can arise from numerous sources, including instrumental instabilities, radio frequency interference, atmospheric propagation effects, and solar system ephemeris errors. Identifying and mitigating these systematics requires careful analysis of timing residuals, comparison between different telescopes and observing systems, and cross-checks using independent measurements. The most subtle systematics may only become apparent after years of observation, requiring ongoing vigilance and analysis technique development. The future of precision pulsar timing promises even more remarkable capabilities as technology continues to advance. Next-generation radio telescopes such as the Square Kilometre Array will provide unprecedented sensitivity for pulsar timing, potentially enabling detection of individual gravitational wave events and exploration of fundamental physics in previously inaccessible regimes. Space-based timing experiments may eliminate atmospheric and ionospheric effects while providing access to frequency ranges unavailable from the ground. The scientific applications of precision pulsar timing extend far beyond gravitational wave detection to include tests of alternative theories of gravity, searches for dark matter signatures, measurements of planetary mass perturbations in the outer solar system, and studies of neutron star physics through observations of timing noise and glitches. Each new millisecond pulsar discovered adds to the growing arsenal of cosmic chronometers available for exploring fundamental physics and astronomy. The connection between millisecond pulsars and atomic clocks has created unexpected synergies between astronomy and precision metrology. Pulsar timing experiments provide independent tests of atomic time-scale stability, while advances in atomic clock technology enable more precise pulsar timing measurements. This interplay demonstrates how extreme astrophysical objects can contribute to the development of terrestrial technology and fundamental physics research. Millisecond pulsars as gravitational wave detectors. The quest to detect gravitational waves ripples in the fabric of spacetime predicted by Einstein's general theory of relativity has found an unlikely ally in millisecond pulsars scattered throughout our galaxy. These rapidly spinning neutron stars, with their extraordinarily stable rotation, function as natural gravitational wave detectors sensitive to perturbations in spacetime over galactic scales and cosmic time scales. The use of pulsar timing arrays to search for gravitational waves represents one of the most ambitious and technically challenging experiments in modern astronomy, requiring precision measurements that push the boundaries of observational science. Gravitational waves interact with millisecond pulsars by causing tiny changes in the geometry of spacetime between the pulsars and Earth. As gravitational waves pass through our local region of the galaxy, they alternately stretch and compress space along different directions, creating small variations in the distances that radio signals must travel from pulsars to terrestrial radio telescopes. These distance changes translate into variations in pulse arrival times that can be measured with sufficient precision to detect the gravitational wave signatures. The sensitivity of pulsar timing arrays to gravitational waves depends on several factors: the timing precision achieved for individual pulsars, the number of pulsars monitored simultaneously, the duration of the observing program, and the distribution of pulsars across the sky. Current pulsar timing array experiments monitor 50 to 100 millisecond pulsars with timing precision ranging from tens of nanoseconds to several microseconds, maintained over observation baselines extending up to 3 decades. This combination of parameters makes pulsar timing arrays sensitive to gravitational waves with frequencies ranging from approximately 1 nanohertz to 1 microhertz, a frequency band completely inaccessible to ground-based gravitational wave detectors. The gravitational wave sources most likely to be detected by pulsar timing arrays are supermassive black hole binaries in the centers of distant galaxies. These systems, with component masses ranging from millions to billions of solar masses, emit gravitational waves at frequencies determined by their orbital periods. During the final and spiral phases before merger, these binaries sweep through the frequency range accessible to pulsar timing, potentially producing detectable signals for millions of years before the black holes finally coalesce. Individual supermassive black hole binaries would create characteristic signatures in pulsar timing data, with specific patterns of timing residuals that depend on the source location, orbital parameters, and gravitational wave polarization. The amplitude of these signals depends on the masses of the black holes, their distance from Earth, and the orientation of the orbital plane relative to our line of sight. The most optimistic scenarios predict timing residuals of hundreds of nanoseconds for nearby massive binaries, while more typical signals might produce residuals of tens of nanoseconds. The stochastic gravitational wave background represents a potentially more detectable signal than individual supermassive black hole binaries. This background results from the incoherent superposition of gravitational waves from thousands of supermassive black hole binaries throughout the observable universe, creating a random gravitational wave field that varies slowly over cosmic timescales. Unlike individual binary signals, the stochastic background produces correlated timing residuals across all pulsars in the array. with a characteristic angular correlation pattern determined by the nature of gravitational wave propagation. Recent results from major pulsar timing array calibrations have provided compelling evidence for the detection of a stochastic gravitational wave background. The North American Nanohertz Observatory for Gravitational Waves NanoGrav, the European Pulsar Timing Array PTA, the Parkes Pulsar Timing Array PTA, and the International Pulsar Timing Array PTA have all reported evidence for a common red noise process affecting millisecond pulsars across the galaxy. While the gravitational wave interpretation remains the most likely explanation, ongoing analysis continues to explore alternative explanations and strengthen the statistical significance of the detect. The data analysis techniques required for gravitational wave detection with pulsar timing arrays involve sophisticated statistical methods that can distinguish gravitational wave signals from various noise sources and systematic effects. The analysis must account for timing noise intrinsic to individual pulsars, correlated noise from solar system ephemeris errors, clock instabilities, and interstellar medium effects. Bayesian inference methods allow simultaneous modeling of all these effects while searching for the specific correlation patterns expected from gravitational wave signals. The computational requirements for pulsar timing array data analysis are substantial, involving the analysis of timing residuals from dozens of pulsars observed over decades with thousands of individual timing measurements. The search space includes numerous parameters describing pulsar rotational evolution, binary orbital motion, and gravitational wave signal characteristics. Advanced algorithms such as Markov chain Monte Carlo sampling and nested sampling techniques are employed to explore this high-dimensional parameter space efficiently. One of the most challenging aspects of gravitational wave detection with pulsar timing arrays is distinguishing genuine gravitational wave signals from spurious correlations that might arise from systematic effects or statistical fluctuations. The angular correlation pattern expected for gravitational waves known as the Hellings and Downs curve provides a unique signature that helps discriminate gravitational wave signals from other sources of correlated timing residuals. However, achieving sufficient statistical significance requires careful analysis of data quality, systematic effects, and alternative correlation models. The frequency evolution of inspiraling supermassive black hole binaries creates another diagnostic for distinguishing gravitational wave signals from noise. As these binaries lose energy to gravitational wave emission, their orbital frequencies increase according to well-understood theoretical predictions. Detecting this frequency evolution in pulsar timing data would provide strong evidence for the gravitational wave nature of observed signals and enable detailed studies of supermassive black hole binary evolution. Pulsar timing arrays are complementary to other gravitational wave detection methods, providing sensitivity to completely different frequency ranges and source populations. While ground-based interferometers like LIGO and Virgo detect high-frequency gravitational waves from stellar mass compact object mergers, and space-based missions like LISA will target intermediate frequencies from intermediate mass black holes. Pulsar timing arrays probe the low-frequency regime dominated by supermassive black hole binaries. This multi-messenger approach to gravitational wave astronomy provides comprehensive coverage of the gravitational wave spectrum. The scientific implications of gravitational wave detection with pulsar timing arrays extend far beyond the confirmation of Einstein's predictions. These observations provide unique insights into supermassive black hole formation and evolution, galaxy merger rates throughout cosmic history, and the growth of structure in the early universe. Gravitational wave detections can reveal supermassive black hole binaries that are otherwise invisible to electromagnetic observations, opening new windows for understanding galaxy formation and evolution. The precision required for gravitational wave detection has driven advances in pulsar timing techniques and radio astronomy instrumentation. Modern pulsar timing arrays require exquisite control of systematic effects, development of new calibration techniques, and improvements in receiver technology and digital signal processing. These advances benefit not only gravitational wave science but also other applications of precision pulsar timing, including tests of fundamental physics and studies of neutron star structure, Future developments in pulsar timing array science promise even greater sensitivity to gravitational waves through several avenues. The discovery of additional millisecond pulsars, particularly those with exceptional timing stability, will improve ray sensitivity and provide better sky coverage. Longer observation baselines will enable detection of lower frequency gravitational waves and improve sensitivity to continuous wave sources. Advanced analysis techniques may extract additional information from existing data sets and improve the separation of gravitational wave signals from noise. The combination of pulsar timing arrays with other gravitational wave detectors creates opportunities for multi-messenger astronomy that could revolutionize our understanding of cosmic phenomena. Supermassive black hole mergers detected by pulsar timing arrays might also produce electromagnetic counterparts observable with optical, radio, or X-ray telescopes. The ability to observe the same astrophysical events through multiple channels would provide unprecedented insights into black hole physics and the environment surrounding supermassive black hole binaries. The technological and scientific infrastructure developed for pulsar timing array gravitational wave detection has applications beyond astronomy. The precision timing techniques, statistical analysis methods, and computational algorithms developed for these experiments have applications in geodesy, navigation, fundamental physics, and precision metrology. This cross-disciplinary impact demonstrates how astronomical research can drive technological development with benefits extending far beyond the original scientific goals. The role of magnetic fields in millisecond pulsar physics. Magnetic fields play a crucial and complex role in virtually every aspect of millisecond pulsar physics, from their formation through binary evolution to their observable properties as precision cosmic chronometers. Understanding the magnetic field evolution of neutron stars during the recycling process that creates millisecond pulsars represents one of the most important unsolved problems in pulsar astrophysics. The dramatic reduction in magnetic field strength, typically from kc Tesla in young pulsars to key Tesla in millisecond pulsars, fundamentally alters how these objects interact with their environments and determines their long-term evolution. The magnetic fields of neutron stars are thought to originate during the core collapse process that creates these objects, though the detailed mechanisms remain subjects of active research. During stellar core collapse, magnetic field lines are compressed along with the stellar material, potentially amplifying weak seed fields present in the progenitor star to the enormous strengths observed. In young pulsars, magnetohydrodynamic instabilities during the collapse may also generate magnetic fields through dynamo processes, while convection in the newly formed neutron star might contribute to field amplification and configuration. Young neutron stars typically possess magnetic fields with strengths of 1012 to 1015 Tesla, making them among the most strongly magnetized objects in the observable universe. These intense fields create powerful magnetospheres that extend far beyond the neutron star surface, accelerating charged particles to relativistic energies and generating the characteristic electromagnetic radiation observed from radio pulsars. The magnetic field structure is generally approximated as a tilted dipole, with field lines connecting the north and south magnetic poles through regions of open and closed field line geometry. The evolution of neutron star magnetic fields over cosmic timescales involves several physical processes that remain poorly understood despite decades of theoretical work. Ohmic dissipation in the neutron star's solid crust can cause magnetic field decay over timescales of millions to billions of years, though the electrical conductivity of matter under extreme density and temperature conditions is highly uncertain. Hall-effect drift of magnetic flux tubes through the crustal lattice may cause field evolution and reconfiguration on intermediate timescales of thousands to millions of years. The recycling process that creates millisecond pulsars dramatically alters the magnetic field properties through mechanisms that are still being actively investigated. Accretion of matter from binary companion stars can bury magnetic field lines beneath newly deposited material, effectively reducing the external field strength while preserving magnetic flux in the neutron star interior. This field burial process may be enhanced by magnetic reconnection events that reconfigure field line topology and reduce the net magnetic flux linking the neutron star to its magnetosphere. Magnetic field screening by accreted material represents another important process in millisecond pulsar formation. As material accumulates on the neutron star surface during the accretion phase, it may form a layer of normal matter that partially shields the underlying magnetic field from external interaction. The effectiveness of this screening depends on the conductivity properties of accreted material and the time-dependent evolution of the accretion flow structure. The interaction between accreting matter and neutron star magnetic fields creates complex magnetohydrodynamic phenomena that influence both the accretion process and magnetic field evolution. Matter flowing from the companion star must overcome magnetic pressure to reach the neutron star surface, leading to the formation of accretion columns where material follows magnetic field lines toward the magnetic poles. The resulting accretion hotspots emit intense X-ray radiation as gravitational potential energy is converted to thermal energy through shock heating. Disk magnetosphere interaction in accreting neutron star systems involves the coupling between the Keplerian accretion disk and the rotating magnetosphere through magnetic field lines that thread the disk. This interaction creates torques that can either spin up or spin down the neutron star depending on the relative rotation rates of the disk and magnetosphere. The detailed physics of this coupling process determines the efficiency of angular momentum transfer during the recycling phase. The magnetic field strengths observed in millisecond pulsars range from approximately 108 to 109 Tesla, representing reductions of 100 to 1,000 times compared to young pulsars. These weaker fields produce correspondingly reduced electromagnetic braking torques, allowing millisecond pulsars to maintain rapid rotation over cosmic timescales. The precise field strength determines the pulsar's spin-down rate, electromagnetic luminosity, and interaction with surrounding plasma environments. Despite their reduced strength, the magnetic fields of millisecond pulsars still create powerful magnetospheric accelerators that generate the observed pulsar radiation. Charged particles extracted from the neutron star surface are accelerated along curved magnetic field lines, producing electromagnetic radiation through various emission mechanisms including synchrotron radiation, curvature radiation, and coherent plasma processes. The specific emission characteristics depend on the detailed magnetic field geometry and the properties of the magnetospheric plasma. The measurement of magnetic field strengths in millisecond pulsars relies primarily on observations of their spin-down rates and electromagnetic pulse profiles. The magnetic dipole braking model relates the rate of rotational energy loss to the square of the magnetic field strength, allowing field strength estimates from timing observations. However, this method assumes a simple magnetic dipole configuration and neglects potential contributions from other energy loss mechanisms such as gravitational wave emission or particle winds. Binary millisecond pulsars provide additional opportunities for magnetic field measurements through observations of eclipse phenomena and orbital perturbations. When the radio emission from the pulsar is eclipsed by material from the companion star, the eclipse characteristics depend on the interaction between the pulsar's electromagnetic field and the accompanying on's atmosphere or wind. These observations can provide information about both the magnetic field strength and geometry in regions far from the neutron star surface. The magnetic field geometry of millisecond pulsars may differ significantly from the simple tilted dipole configuration assumed in many theoretical models. Accretion-induced field evolution, crustal fracturing due to spin-up stresses, and magnetorotational instabilities may create complex multipolar field structures that affect emission characteristics and magnetospheric dynamics. Recent numerical simulations suggest that millisecond pulsar magnetic fields may exhibit significant departures from dipolar geometry, with implications for understanding their emission properties and evolution. Magnetospheric physics in millisecond pulsars operates in regimes that differ qualitatively from those in young pulsars due to the combination of weak magnetic fields and rapid rotation. The light cylinder radius, the distance from the rotation axis where the corotation velocity equals the speed of light, is much smaller for millisecond pulsars, creating more compact magnetospheres with different particle acceleration regions and radiation zone geometry. These differences may explain some of the observed distinctions in emission properties between millisecond and ordinary pulsars. The role of magnetic fields in determining millisecond pulsar emission characteristics remains an active area of research. The observed correlation between magnetic field strength and radio pulse width suggests that field geometry influences the size and location of emission regions within the magnetosphere. Multi-frequency observations reveal frequency-dependent pulse profile evolution that may reflect the radial dependence of magnetic field strength and the altitude structure of emission regions. Above the neutron star surface, magnetic field evolution continues throughout the lifetime of millisecond pulsars through various physical processes operating on different timescales. Continued ohmic dissipation may cause gradual field decay over billions of years, while magnetic reconnection events triggered by crustal motion or external perturbations may cause sudden field durations. Understanding these evolutionary processes is crucial for interpreting the observed properties of millisecond pulsar populations and predicting their future behavior. The connection between magnetic fields and gravitational wave emission from neutron stars represents an emerging area of research relevant to millisecond pulsar science. Magnetic field stresses in the neutron star crust may create small asymmetries in mass distribution that generate continuous gravitational radiation as the star rotates. The amplitude of this emission depends on the magnetic field strength and configuration, making millisecond pulsars with their precisely known rotation rates ideal targets for gravitational wave search. Future observations of millisecond pulsars promise to provide new insights into magnetic field physics through improved timing precision, multi-wavelength studies, and advanced polarimetric techniques. Space-based X-ray observations may reveal thermal emission from neutron star surfaces that depends on magnetic field-induced heating, while radio interferometry could potentially resolve magnetospheric structure nearby millisecond pulsars. These developments will advance our understanding of magnetic field evolution and its role in determining the observed properties of these remarkable cosmic laboratories. Millisecond pulsars in binary systems. The majority of millisecond pulsars exist in binary systems, bound gravitationally to companion stars that played crucial roles in their formation and continue to influence their evolution. These binary millisecond pulsar systems provide unique laboratories for studying stellar evolution, gravitational physics, and the exotic behavior of matter under extreme conditions. The diversity of companion types and orbital configurations reveals the complex evolutionary pathways that lead to millisecond pulsar formation, while offering unprecedented opportunities to test fundamental physics in strong gravitational fields. Binary millisecond pulsars can be broadly classified based on the nature of their companion stars and the characteristics of their orbital motion. The most common category consists of systems with white dwarf companions, typically low-mass helium white dwarfs with masses ranging from 0.15 to 0.45 solar masses. These systems represent the end products of the recycling process, where the original companion star has been stripped of its hydrogen and helium envelope through mass transfer, leaving behind the exposed stellar core as a compact white dwarf remnant. The orbital characteristics of binary millisecond pulsars reflect their evolutionary history and provide insights into the mass transfer processes that created them. Most systems exhibit nearly circular orbits with eccentricities less than 10 to 3, indicating that tidal interactions during the mass transfer phase circularize the orbits. Orbital periods typically range from a few hours to several hundred days, with the distribution showing distinct peaks corresponding to different evolutionary channels and companion types.